So I'd like to do a quick introduction to the idea behind double integrals. So let's consider a picture first to get started. So here's an axis, x, y, and z is our vertical axes. And let's pretend we have some surface floating up above the xy plane that looks maybe something like that. And this could be z equals f of x comma y. Okay, so what we're going to do is we're going to integrate over a rectangular region. So I'm going to say that x is bounded between a and b, and then y is bounded between c and d. So if we were to trace across here, what we would notice is something like this. So we have, now these dotted lines really go on forever, but we have a rectangular base right here that we're integrating over, okay? And the premise behind a double integral, at least for the Riemann sum idea behind them, is the following. You create a partition of this region. So maybe you do that by creating 6 rectangles like this. Okay, and let's just consider one rectangle by itself, this one. And for those of you who are thinking back to integrals in 2 dimensions, you learn things about LRAM and RRAM and all things like that, nice rectangle approximation methods. You don't have perfect analogies in this up a dimension in the 3-dimensional world, but you could call these rectangular prism approximation methods. But if you think about it, this thing here, this little blue rectangle I've drawn, represents the base of a solid. And to get the height of the solid, just like you'd back in the 2D world, you took the height of the function. You do the same thing here. So I'm going to pick the lower left corners and trace them up till I hit the surface. And right here is the point f of a comma c. There's a z value associated with that. So I'm going to choose that to be the height of my first rectangular prism. And now what I'm going to do is I'm going to copy that height over again 3 more times. Here, here, and here. And what you end up with is this first rectangular prism. That first rectangular prism is the beginning of an approximation to the double integral. So now, what happens next? Well, we'll go over here to this rectangle. We'll do the same story. Maybe we'll pick the lower left corner again, which I should mention, you don't really have to. You could pick any. Trace that up to the curve, and maybe this goes to some higher point on the curve. And then what I'm going to do is I'm going to copy that height over again in these other locations and create a second rectangular prism, which would also have volume. Now, we can think of this as the following. What you really want to do is add up all these rectangles. Well, they have dimensions of the following. So we look at this rectangle. This piece, this side of it would be delta x. This side would be delta y. And then the height is f of x comma y for some x comma y inside of this little rectangle here, or maybe the lower left corner like I've designated. So what I want to do is I'd like to add up all of those areas. And basically that's what a double integral does. It says, hey, double integral from a to b, c to d, f of x comma y, comma dx dy. You'll always need to set an order for your integral. But basically, this is an introduction to it. We can write this as the following. We can say it's the sum of f of x comma y d delta x for all the xi, and then add that from 1 to n maybe, and then some other I equals 1 to m delta yi. And then that turns into this, double integral. You're adding up many, many, many rectangular prisms until you get the exact volume.